Okay, let's start. Good afternoon. So this week we're going to start discussing iterated function systems, and we're going to start using these ideas about metric spaces that we've developed, hyperspace and everything, to really start talking about fractals in a very formal way. Now there are 5 perspectives that you might approach an iterated function system from. For now, we're just going to focus on the first two, this monoid or semigroup approach and the Hutchinson operator. And then I'm expecting that when we start talking about topological dynamics, we're going to start using this idea of a cocycle, and we're going to start thinking of iterated function systems as certain cocycles. And then we're going to do some dimension theory, and then we're going to come back and we're going to start talking about measure theory a little bit, invariant measures and stuff. And there we're going to really start thinking about random walks and Markov operators. Okay, but for now we're just going to focus on this and this. So let's first talk a little bit about these monoids and groups and everything. This is there are certain algebraic structures. And really, since we're thinking about dynamics, we should be thinking of monoids or semigroups of transformations. And so I start with a set. And then I can look at the set of all functions from x to itself. Okay. Now, this set is not only a set, but in fact, this is a monoid, is what we're going to say. And this means that you have a certain operation defined on this set that allows you to combine 2 functions. Any guesses as to what that operation could be? Right. So if you have 2 functions, you can compose. So, is a monoid under function composition. So let's write it like this. If I have one function from x to itself, which is, let's call it f, and another one, let's call it g, then the composition of them is typically denoted by GOF, and it is defined like this. So what is this? Well, first apply f to x. That gives you another point in x, and then apply whatever outcome you have, apply to that g. Now there's a bunch of like axioms and stuff like that that I'm not going to discuss. They're rather straightforward. If I were to instead look at not only functions from x to itself, but invertible functions, in other words, bijections from x to itself, that gives you a monoid. A group. So if you have a bijection from x to itself, then you can also invert. Right? So you have a composition operator, and then you have an inversion operator as well. So let me denote it like this. And say bij of x is the set of all those functions from x to itself such that f is invertible. So there's another function that is typically denoted by F inverse, such that F composed with F inverse is the identity function, and vice versa. You can change the orders as well. It's a group. Okay, now I don't want to go too much into the technicalities and formalisms of all these objects, but if you take a class in group theory, you spend a lot of time about these things. Let me just give as exercises finding the definitions of certain things. Define submonoid, monoid, and subgroup. And let me also give the definition of, or the definition of an abstract monoid or a group as an exercise. Abstract. Any questions so far? Yes.
I think maybe my question is the exercise in a sense of saying, is our definition for a monoid here just the set of all functions that map x to itself? Or?
Yeah, I mean, this is really an example.
Really
I'm saying that
okay.
If x is a set, then the set of all those functions from x to itself is a monoid.
Okay.
And I'm saying, oh, there's a composition, and I'm sort of being, I'm not really telling you what the definition is.
Okay.
The exercise is to find the definition. Yeah. I think it has to be associative, blah, blah, blah. It has axioms, basically. So one thing that is, of course, important, I mean, subgroup, what could it be? It's like a subgroup of the bijections. Well, it's going to be a subset that is closed under function composition. So for instance, I can start with the group of bijections of the real line. But I can, yes?
Can you remember what the definition of what a bijection is?
It's a function, so bijection means...
Actually, it's written right there.
Yes, there's a functional inverse.
Okay.
Yeah. Yeah, so maybe I should put here. That's a bijection. It satisfies the horizontal and vertical line rules. If you cut the graph like this, it hits exactly once. If you cut it like this, vertically, it hits exactly once. Bijection. Not a bijection. Doesn't satisfy the horizontal line test. Okay. Any other questions? Okay, inside this I can look at the subgroup of all homeomorphisms, for instance. Now what does that mean? That means that if I were to take two homeomorphisms of the real line, and if I were to compose them, okay, the composition of continuous functions is continuous and blah, 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 which means that this indeed is a subgroup. It is closed under function composition. Or I can go even further. I can say something like, let's write, I'm going to write Lipeo, for instance. By Lipschitz homeomorphisms. It's a subgroup under composition, and so on. Maybe I should put here this as well. So here's a definition. So this F of R is the group of affine transformations of the real line, which means that any bijection here, after all, it's a subgroup of this, is what I'm claiming, but it's of a very specific type, which is this. Okay. So take x and send it to ax plus b, where a is one fixed number and b is some other fixed number. So you get to have translations. If you were to fix a to be 1 and b any number, you would have translations. And you also have scaling. And if you were to take two functions like this, and if you were to compose them, you're going to get another function of this form. And it's the inverse of a function like this is also of the same form. Okay, so that's what it would mean for f of r to be a subgroup of bijections. And then even smaller than that, you have the group of linear transformations, which is denoted by GL of R. General linear, that's the abbreviation for it. And so what is this? This is this. Okay, you have all these different types of groups. So whenever you sort of specify a certain property, you typically go to a subgroup, which means that your group sort of like gets smaller, it shrinks, but at the same time, you have more properties that you can use. Yes?
When you're talking about size, are you talking about cardinality of these different things?
In the sense of inclusion.
Inclusion, okay.
Yes. Okay. Any questions about anything here? Okay. Okay, now we can give the definition of an iterated function system. In general, let x be a set. An iterated function system on x iterated function system IFS for short, is a subset of f of x comma x. W it's as general as this. Now, this is too general, as you might realize, and we really don't have much to say here. But perhaps tomorrow or on Thursday, we're going to sort of specify to a class of iterated function systems that we're going to use. But still, I thought it would be good to sort of give this abstract definition, because indeed, this more specific type of IFSs that we're going to spend more time on, people have generalized them and they've used the same idea in different settings. So I wanted to sort of give this more abstract definition. Now, what I can do is I can look at, okay, definition. If I have an IFS on X, I can look at the monoid generated by that set, by that IFS. So let's take a subset. Then I'm going to denote it like this. W in brackets. This is going to be a submonoid of this guy. And so a monoid is supposed to be closed under composition, but a set of functions doesn't need to be a priori, which means that all you need to do is you take functions from this W, from this set that you chose, and you keep sort of like putting all the compositions you have. So let's say your set is like this. Let's say that you have two of them. Then this monoid would be something like this. You have to have the identity. Then you're going to have these functions. Then you want to have W1 squared. So W1 applied to itself. Then you're going to have W1 composed with W2, and then W2 composed with W1. And these two might be different functions after all, so you have to put them in. And then W2 squared, and so on. This is an infinite set in a sense. Okay. So here's an example. Let's take x to be R, the real line. And really, I'm going to take elements from this affine group. Example. Let's say that my first function is x over 3, so scaled by a factor of 3. And W2 of x, I want to be x plus 2 over 3. So this is an affine function. And so I can take these and put them in a set. Okay, now this is a subset of the affine group. And so what is the monoid generated by these two? Well, I need to just keep writing the iterates, right? So I have the identity transformation, which is just take x to itself. Then I have W1, which is x over 3, W2, which is x plus 2 over 3. Then I need to compose W1 with itself. So W1 squared of x, which is the same thing as W1 composed with itself. Okay, so now the point of this example is to come up with the explicit formula. Well, you can sort of like do it either way, but if you were to open this up, this would give you W1 of x divided by 3. I just use this, right? Because W1 just divides whatever you feed to it by 3. And then, but this is x over 3, which means that this whole thing is really x over 9. Any questions about this?
Can I just
Yes.
make sure that, like an alternate definition or maybe part of this definition, it's like the smallest monoid containing.
Exactly.
Okay.
Yes. It's smallest in the same sense that we discussed before. Generated by, like we were talking about the smallest, for instance, the closure of a subset, right? We were saying it's the smallest closed set. Take all the things and then take their intersection. Let me not write it. And then if I were to look at the next guy, which is W1 composed with W2, and get this. Okay, you can again open this up in two different ways. Let's start with this. So I want to start with W2 of x, and then I'm going to apply W1, which means that I need to divide whatever this is by 3. But then if I were to plug this in, I get x plus 2 over 9. Okay. If I were to do it the other way around, you see now this you're going to get a different function. So this is going to be W1 of x plus 2 over 3, which then is x over 3 plus 2 over 3, which then if I were to consolidate everything, I would get x plus 6 over 9. Okay, let's do one more. I think at this point you get the idea. W2 squared. Okay, so if I were to consolidate, I get x plus 8 over 9. And you keep going, okay? As you see, I just opened up the definitions of the first couple of functions in my monoid generated by the iterated function system. And as you see, at each step, I get something somewhat different. I'm not saying that this has to be the case all the time, but typically, this is the types of iterated function systems we're going to look at. Any questions so far? And you see, if I keep going like this, I don't necessarily have sort of like an explicit expression of W1 to the 15, then W2 to the 75, blah, blah, blah. But ultimately, this is a well-defined object. I'm saying whatever compositions you have, put all of them there. This is something that you claim that you're allowed to do in math, okay? Some people don't like these kind of things, but for us, there's no problem in sort of coming up with this object. Okay? Yes?
So when you're generating that, do you have to do it both ways?
Yes.
Okay.
Typically, exactly. Yes, that's an important point. So what your colleague is saying is that you have this, which gives you this. But if you were to switch the orders, you get a different function. Okay. Okay, so the next definition is the notion of a group or monoid action. Or even before that, maybe I should define the notion of a homomorphism. Let's have two monoids or groups. A function between them is a monoid or group homomorphism. If it respects the operations. So now, if these are abstract, groups or monoids, you have something like a multiplication that works like this function composition. So I want to say something like, if I were to take two things, compose them, or multiply them, and apply my function, I want this end result to be the same as this. Okay, and a monoid or group action on X is a homomorphism from G to either this or this homomorphism. I'm going to give examples of this in a second. One sort of like nice notation for this is this. You also write something like G and then this, curved arrow X. Especially if you don't want to sort of like worry about these, bijection or homeomorphism, blah blah blah. If you want to be sort of like more, closed in a sense. If you want to suppress notation, this is sort of like a very common notation. Okay. So here are more examples. I wrote some examples here. Okay. This is the monoid of non-negative integers. What does that mean? It means that, so what is the operation? It's addition, of course. If you were to take two non-negative integers, add them up, you get another one. Okay. Let's send it to the monoid of all functions from the interval to itself. Well, I need to say what happens to n. This is sort of like my time, if you want. This is my time. This thing is my space. I'll send it to f to the n, where f is nothing but this sawtooth function, which is this 2x mod 1. Okay, this is an example. So we were discussing this last week, and when it comes to dynamics, typically people look at one function, but really when they are looking at one function, one map, they look at the iterates of it. In other words, they look at the action generated by this. So let me remind you how this looked like. So this is my diagonal, and somewhere here is 1/2. Like this. This is my f. Okay. Now what is f squared? F squared is f composed with itself. Let's also try to understand this. Any ideas as to how I can sort of think of this function more explicitly? If this is sort of what is happening in time 1, what happens in time 2? Yeah.
4x mod 1.
Exactly, right? And in general, at time n, this really is 2 to the n times x mod 1. Any questions about this? This is a very important example. It's very simple in a sense, but it's also a very deep example.
So we're claiming this is a homeomorphism, or we're claiming this is a monoid, or we're claiming that?
I'm not saying it's a homeomorphism because it doesn't satisfy the horizontal line rule.
That makes sense.
Okay. But it is a perfectly valid function. It's not even continuous the way we wrote it, but it's a function from the interval to itself. And I can keep iterating it. Okay. I'm aware I just like threw out you a bunch of new definitions, or I didn't even say the definitions, but I started using definitions. But part of dynamics is to just hear something and go with it without worrying too much about the background. Okay, so here is another example. So this, let's call this sawtooth. Or another name for this is the doubling map, because you double whatever you have. Let's look at this. Now I can look at now this is the pair of non-negative integers. So an element here is of the form n comma m. Both of them are integers. And of course I can add both of those if you want as vectors, and that gives me another element. So this is a monoid. And again, let me look at this. And so if I were to take this, n comma m, I want to send it to a transformation. And I'm going to send it to f to the n composed with g to the m, where f is that guy. And g is 3x mod 1. Okay? This is what is called the times 2 times 3 map for obvious reasons. So what I want you to think here is that whenever I have an action like this, whatever I put here is really my notion of time. This is somewhat more intuitive in a sense. I have a one-dimensional time. It's discrete, but we're familiar with stroboscopic times, like a film strip. But this too is a perfectly valid notion of time for us. Okay. So somehow here, our notion of time is like this, whereas here the notion of time is sort of like a two-dimensional. We can go sort of rightwards if you want to apply f, or you can go upwards. So in a sense, sort of one way to think about this is that you have sort of like a standard film strip, and you look at what happens scene after scene, frame after frame. Somehow here you have a whole plaque of film, which you can read this way or that way. Now I'm not claiming that there's a machine that can run this, but sort of that's one way of thinking about it. And somehow you get to sort of like go both ways, either ways. Okay. Any questions about these so far? Okay. Here's another example. These were so far continuous time, and in this class we're going to spend we're going to sort of just look at discrete time typically, but we can look at continuous time as well. And so differential equations, or ordinary differential equations if you want, fall into this category, this continuous time dynamical systems or actions. Let's look at this example. Let's write it like this. dx by dt of t equals x of t. So here, x is supposed to be a function, let's say, from reals to itself. And this is what is called an ordinary differential equation. How many of you have seen something like this before? Okay. then let's just say that if you have a function like this that satisfies this differential equation, then this says that x of t really is of the form e to the t times some constant. Right? The only function that satisfies that equation is constant multiples of e to the t. Now, what is this constant multiple? What does that c? That c really is the initial condition. So if I were to say x of 0 equals, let's say, x sub 0, then I can write it like this. Okay. But then this right-hand side, if I wanted to keep varying the initial condition, so I can think of it as sort of like another variable, this function depends on two things. So maybe it's better to write it like this. Okay. Now, this, if I were to look at what happens at t plus s time, so the initial condition x0, if I were to just plug in, I get this. But then exponentials split additions to multiplications, which means that I can write this like this. But then this guy right here is nothing but x of s comma x0. But then I can, again, sort of write this like so. What this really says is that you have a group homomorphism again. From the reals, this is a group under addition after all, to, let's say, the set of bijections from the reals to itself. Because multiplying any number by some number is a bijection after all, because e to the t is always non-zero. Take time t and send it to the bijection, which is a time t map, is what is called, of this solution. So you see now, somehow I'm fixing the time and I'm varying the initial condition. This is an operation that takes any initial condition that you want and moves it according to the differential equation by t time. This is yet another this is yet another group action. Yes?
Is our binary operation on the reals, is it multiplication or?
It's addition here. And here it is function composition. Yes. Okay. Now, the formalism here is slightly different than the formalism that I started with. So here's an exercise, is a formal exercise related to this. Okay, a couple of exercises perhaps. This is what is called the adjunction operation, or computer scientists use the word unCurrying. Curry was a computer scientist, logician, many things, which basically says this. If you have three sets, let's say x, y, and z, by taking the products, you have another set, and you can look at the bivariate functions from x times z to z. This is really the same thing as the functions that starts with x, and to each x associates a function from y to z. Okay. So I have a function like this here, but this really I can think of as take x, send it to that function that takes a y, and sends it to f of x comma y. Based on this, you can think of a group action or a monoid action if you want it, this way as a homomorphism, or as a certain function from g times x to itself. And so here, really in this differential equation notation, the moment I said, oh, I'm going to put this initial condition as one of the inputs, I sort of switched over to this notation. Okay, these are sort of like things that you learn when you take a class in group theory. But for us, this is basically formalism. Okay. Questions about any of this? Well, this idea is very important, for instance. When you're first defining partial derivatives in multivariable calculus, you have a function that depends on two variables, and then let's say that you have a function that depends on x and y, and then you say, I want to define the y partial, for instance. Well, how do you define it? You fix an x, and you think of the function as a function that depends on y, and then you take the single variable derivative. Okay, this is sort of like the formalism behind all this business. If this is if you're not liking any of this, it's not a major problem. Oh, here's a nice example. Let's sort of start thinking about this hyperspace as well. For instance, I can do this. I'm going to use this notation. Let me let X to be the hyperspace of reals, so the compact non-empty subsets of the real line with the Pompeo-Hausdorff distance. And let's look at this action. So I need to tell you what happens at time 1. Because once I tell you what happens at time 1, you know what happens at any time. It's just the iterates. But let's say that at time 1, this is what you do. Take a function, take a set, which is a point in x. Maybe I should use a different letter. Curly x. And just take the union of the set with the interval 0, 1. Now this is a Lipschitz function, in fact. So exercise is Lipschitz. So this is this idea of condensation. Later on, probably on Thursday, we're going to call this set the condensation set of the iterated function system. So this is related to condensation. Okay. Yes?
Could you explain the error notation one more time?
Oh, it just means that this guy is acting here on this thing. It keeps moving. Yeah. Another notation. So especially if this is your monoid, another notation for this is you say this. You write it like this as well. These are both like things that you often see in the literature. Okay. That's okay. Let me give an example, an exercise. So we had this. Let me remind you. This was an example that we just discussed. Now, a nice exercise would be to likewise write down the sort of some of the elements in the monoid generated by an iterated function system, where now I'm going to look at a different iterated function system. So write some elements of W, let's call it W prime, I'm just going to leave it like that. Where I'm going to keep the first transformation this way, but let me use as a second transformation this 1 minus x divided by 3. Okay, now I'm taking, instead of this guy, I'm taking this guy. And then I generate the monoid, and I want you to sort of write down some of the elements in this monoid generated by this iterated function system, which means that you want to take a couple of these and then a couple of these, and then you want to sort of put them together to get another sort of affine function like this. Okay, just to get a sense as to what is happening. And as you can see, even though I use the same notation, this iterated function system is not the same iterated function system as this. Okay, they are different functions. Okay, this function is different from this. Questions about these?
Question on the left board.
Yes.
When you say phi is Lipschitz, is that the same as saying that it's a Lipeo-morphism?
No.
It's not? Okay, so I guess I'm confused. Can you tell me more about how phi is Lipschitz?
Well, so you want to say something like this, right? Saying for some c, this is true. Okay. In fact, you can do this with c equals 1, but yeah. Any other questions?
Specifically this one, we're still using x as the reals, right?
Yes, yes, yes.
Okay.
Yes.
So,
Yes.
on the left board, I guess we're not specifying what the homeomorphism is, and that's why we're just calling it a group action.
Well, it's a monoid action. I'm not saying invertibility. There's no backwards time. I don't care about inverting. Now, there are things where you can sort of like get a group action from this, but that's too abstract and we don't need it. So we're not gonna look at that.
So phi is just I guess, is phi the binary operation on the, I don't
Okay.
know what my question is yet.
If A is a compact subset of the reals, if I were to take the union of it with the 0, 1, that's still another compact subset. Okay? So if I were to feed to phi 1 point, it just puts 0, 1 as well.
Gotcha.
Okay? So this is not invertible, for instance, because there is no A such that this is the interval from 0 to 1/2, for instance. Okay?
I'm with you now.
But I can go forward. I can keep sort of, and of course, okay. What is phi squared of A? Phi of A, right? Because if you just add 0, 1 to whatever set once, well, I mean, you're not doing anything else. If you want, it doesn't matter how many more times you're going to try to add this thing to this set. It's just going to stay the same. So this is what is called it's called an idempotent operator. It's almost like a projection if you want. Okay, let's take a 5-minute break and then when we come back, we're going to continue. Okay, welcome back. Now, I know that I've raced through all this background stuff, but at this point, I think it would be a very good idea for you to start reading chapter 3 at the very least in the textbook, where he's really talking about very specific examples. I will spend a little bit more time on certain examples as well, but I'm going to sort of keep pushing. So we defined iterated function systems very generally, but at the very least, the space, the set X on which we're defining an iterated function system should be a metric space, and then so that we can sort of start using this, all the machinery that we developed. But before that, here's another definition, which I could have defined in week 1, but I sort of postpone this a little bit. So if I have two metric spaces x and y and a function from x to y, then I define its Lipschitz constant, which I denote by lip of f. This could be infinity as well, but as this number. Okay, I look at any 2 points, x1 and x2 and x, that are not the same, and then I look at this rise over run ratio, basically. Okay, this is almost like a derivative type of thing, but it's not quite. But in a sense, it turns out that this is sort of like a metric space analog of the notion of a derivative, if you want. I take 2 points that are not the same, and I look at the ratio between the distances, the distance between their images and distance between them. Okay, so here's an exercise. You can also write it like this. In a sense, this Lipschitz constant is the best constant in the Lipschitz property. Okay, recall that Lipschitz property said this. There is some c such that for any x1 and x2, this happens. So the Lipschitz constant is the best c like this. Because, as I hope you would agree, if for some c this is true, I can keep increasing that c. But there's a minimum c that this happens, if at all. It's the best optimal c. And so what is the exercise? The exercise is that this is really, let me write it here, the infimum of all those, actually the minimum, of all those numbers, c positive, or non-negative, such that this happens. So you look at all the you look at the set of all those C's such that this happens for any x1 and x2, and then the best one out of them is the Lipschitz constant, and somehow you can define it like this or like this, and they are the same number. Okay. Of course, I'm not saying at this stage that the function f is Lipschitz, which means that a function f is Lipschitz if and only if its Lipschitz constant is in fact a finite number. Okay, so do any of you remember the definition of a contraction? This was something that I defined, I think, in week 1. What is a contraction?
Isn't it just if like c is less than 1?
Exactly. So one way of saying this, using this notation, would be that the Lipschitz constant is less than 1. Contraction, if and only if it is Lipschitz, but further, its Lipschitz constant is less than 1. Okay. So this means that under F, points sort of come closer. Okay. So with this, I can now give the more specific definition of an iterated function system that we actually will be able to say something about. Okay. Now in the book, Barnsley calls this hyperbolic iterated function system. And here, hyperbolic should remind you of this stretch and fold business, okay? Last week we sort of had these examples. It's in the same paradigm. I'm not going to call it hyperbolic because some people call it, for instance, contractive iterated function system and everything. Instead, I'm going to call it iterated function system in the sense of Barnsley, and I'm going to say B-IFS. And once I go through some of the papers that I've found, I'm going to put some of them on Canvas in case you're interested in sort of these generalizations. And IFS in the sense of Barnsley, and indeed, even though he wasn't the first person who looked at these kind of things, he certainly was the person who came up with the name IFS, and he popularized this idea. And IFS in the sense of Barnsley, which I'm going to write as B-IFS, BIFS, is, let's write it like this. Say complete metric space and W is a finite set of contractions of X. Okay, so of course a BIFS is also an IFS, but not necessarily vice versa. And the example that I gave you before this is a BIFS, okay? Are we all comfortable with this idea? That this, okay, so X is a complete metric space. We didn't prove it, but let's, take that for granted. And both of these are contractions because they contract distances by a factor of 3. So, okay, any questions about this? Now, in general, the space doesn't need to be a complete metric space. It doesn't even need to be a metric space. W doesn't need to be a finite set, nor does it need to be a contraction, a set of contractions. But at least for what we're going to discuss, at least for this week, and if you read the book, this is sort of like the type of iterated function system that we look at. So these are also called hyperbolic or contractive iterated function systems. Okay. Now, in this example, both of these transformations contract by a factor of 3. But in general, even for a B-IFS, your contraction constant doesn't need to be the same, okay? So here's another example. For instance, let's say okay, let's do 1/5 here, 0, and then let's take 3/5 to 1, okay? Or something like this. So if I wanted to write this down, I would write it like so. Oh, let's do it like this. Okay, I'm going to leave it like that. So I'm going to shrink by a factor of 2/5 and then add this. So this would be 2x plus 3 divided by 5. This is again a B-IFS. Now the contraction here is 1/5. Here it's 2/5. This doesn't contract as much as this does. But still, I can put these two in a set, call it uppercase W, and that would be a B-IFS for me. And if I wanted, I could have put more functions in it. I also don't need to have exactly 2. Okay. And in fact, they also don't need to sort of separate. Here's another example. Yeah, for instance, this. How many of you at this point can start seeing sort of like the connection with the sorts of things like the Cantor set when I'm looking at these kind of objects? At least when I'm starting to draw this, right? It's like you can think of it like this as well. But how about this? Somehow, if I were to look at what happens to the unit interval, I wanted to do something else actually. Let's do 2/3, and okay, I'm going to use 2 functions actually. One might 3 minus 2/3, 3 minus 2x/3. So somehow, if I were to apply W1, I get this piece. I mess up. No, that's correct, I think. And if I were to apply W2, I get this. So somehow they have something like an overlap. So this is also perfectly valid. I'm contracting. Insofar as I'm contracting things, that's fine. That's a B-IFS or B-IFS. Okay. Any questions about these? Now, given a B-IFS, there is an induced operation or operator on the hyperspace of the space. And that is called the Hutchinson operator. So far we talked a little bit about monoids and groups and stuff. So now this is sort of like the second perspective that I mentioned that you can use for iterated function systems. Okay? If I start with a B-IFS on X, which means that this is a complete metric space, so I'm not going to write it after, over and over. And this is like finite to many functions, and each of them is a contraction for X to itself. So let's write it. Let's say, I can just write it like this. For any I, the Lipschitz constant of the ith function that I chose in my B-IFS is less than 1. That's the definition of B-IFS. The Hutchinson operator of this B-IFS is a certain function defined on the hyperspace of X. Of is, so I'm going to denote it by h of w, and that acts on the hyperspace of X. So you feed to it a compact subset, gives back another compact subset. And how is that defined? Well, you take a set here, let's call it A, apply each and every single one of these functions to A, then take their union. Okay? Now, is this well defined? Well, if I were to take a compact subset, and if I were to apply to this compact subset a contraction, well, a contraction is Lipschitz, which means that in particular it is continuous, which means that this is the continuous image of a compact subset, which means that in particular this is a compact subset in and of itself. But then, if I take, finite to many compact subsets, take their union, that is also a compact subset. So this is well defined. It's a well defined transformation that is acting on the hyperspace. Now, from this perspective of monoids and stuff like that, really, I'm not looking at this guy once. I'm thinking of iterating this. Okay? I want to keep iterating this thing inside this hyperspace. So here's an example.
Can I ask a question?
Yes.
I'm having trouble understanding what the hyperspace of W means.
It's not, no. This is the notation. I'm saying it's like the operator induced by W at the hyperspace level. That's what I'm trying to say.
Okay.
Yeah.
Is it okay to think about it as like this is like the Hutchinson operator of this?
This is the Hutchinson operator. This is the definition.
Yeah.
This, yeah. Example. It's a complete metric space. Again, I'm using the standard example. This is a B-IFS. The contraction is 1/3. What is the Hutchinson operator? If you take any subset that is compact inside the reals, well, you're going to take the union of, maybe this doesn't make sense, but take the set, scale it by 1 over 3. That's a compact subset. Take the union of it with this plus 2 over 3. Take the set, scale it by 1 over 3, and then shift to the right by 2 over 3. Now, this doesn't quite make that much sense, but if I were to feed to this Hutchinson operator, A equals the unit interval, which is a point in the hyperspace after all, this is what I get. So now, what is this part? This scaled by a factor of 3 is 0 to 1 over 3. Union, if I shift this interval by 2 over 3 to the right, I get this, which is exactly the first step of this Cantor set construction. Okay? If I were to apply, again, you see, I have one map, but from a dynamical point of view, I'm not going to just apply it once. I'm going to keep applying it. If I were to look at the second iteration, h of w, the Hutchinson operator associated to the B-IFS, to the 2, so I'm applying it twice. This is the same thing as applying the Hutchinson operator to this compact subset. I'm leaving it to you to write this explicitly. So you should start with 0 to 1 over 9 and then blah, blah, blah. Okay? And as you can, I hope, see, or discover eventually, that really this function, so this set, the second iterate of the Hutchinson operator applied to the interval 0 to 1, really gives you this second stage of this Cantor set construction. But you see, this B-IFS business really sort of opens up a whole horizon. Now, like, I'm not even saying at this stage that I have to start with the unit interval. I could have started with, some other interval. But here's an important idea. In this case, for instance, the Cantor set that we've been looking into a little bit really is a fixed point of this Hutchinson operator. So let me write it here. Is a fixed point. Of the Hutchinson operator. What do I mean by this? It should be a set A, or C, I guess, such that if I apply the Hutchinson operator to C, I get back the same function, same set. Yes?
Can you say that it's the largest fixed point?
It's the only fixed point, actually. It's actually the unique fixed point. And I'm running out of time, but the point here is, maybe I should just state it. This is based on a more general statement. Let me just write it over here. And now we have the big theorem for this part of the class, which is the Banach contraction principle, which says that any contraction on any complete metric space has a unique fixed point. Next time we're going to prove this. complete. F x from x to itself, contraction. Then there's a unique fixed point. Here's a new symbol. There exists. When you put the exclamation mark, that means unique. Next time we're going to prove this and apply it to the Hutchinson operator. Okay. Now it's not clear at this stage that this Hutchinson operator is a contraction relative to the Pompeius-Hausdorff distance, but that's also something that we're going to prove. Okay. And that's it for today. Thank you. Okay, I think it's time. Hello. Good afternoon. No, sorry. So today, we're finally going to have this iterated function systems generating fractals for us. We're going to justify all this Cantor set construction and everything. And we're going to prove this big theorem for this part of the class as well. Now, this part of the class I called iterated function systems. So this is sort of like the part where we introduced this idea, but we're going to keep coming back to this. This is like one of the important examples for this, or this class of examples for this class. Before that, I wanted to mention two things. And so this is about different type of times and how that would sort of like, how those would work. So there's like a very nice novel by Alan Lightman, which is like a very nice name for a physicist, I guess. So he's a physicist and a novelist. So he has this book, Einstein's Dreams, and it has a bunch of like different stories, and each of them is supposed to be like one of the dream of Einstein, and he's imagining sort of like a different notion of time and how things would work and so on. That's one. This is sort of like more on the pop side. On the more serious side, there's something called 2T physics, and one of the main guys who does this is Itzhak Bars. So he's looking at sort of general relativity, where the notion of time is two-dimensional. So people are looking at, different notions of time. I just wanted to mention this. It's not just a pure abstract idea. Well, maybe it is, but at least some people are who are not doing abstract math are interested in these kind of things. And there are variations, like circular times and blah, blah, blah. Okay, so let's recall some ideas. So I defined this thing called the B-IFS, Barnsley RFS, or IFS in the sense of Barnsley, which Barnsley calls hyperbolic, iterated function system, but still. And so by this I mean I have an x, which is a complete metric space, and I have finitely many functions from x to itself, such that each of them is a contraction. So this Lipschitz constant, recall, was sort of like the best C you could put in the Lipschitz property. I want each of them to be a contraction. And in terms of these monoids and stuff like that, we had this set, and we looked at the monoid generated by it. And so this I would like to think of as a time, and it's acting on this space X. Okay, let's look back at this Hutchinson operator business. So if I have a B-IFS, the Hutchinson operator basically took all of these contractions in your B-IFS, and it puts all of them into one thing. But it acts on the hyperspace, not on the X itself, but on the hyperspace, which acts like this. If you take a set A and apply your Hutchinson operator, well, the outcome should be nothing but taking A, applying each of the contractions, and then taking their union, okay? Now, here's sort of like this dichotomy. When you think about this, this is also a dynamical system, but the time is the iterates of the integers. It's just a non-negative integers. So you see there's a trade-off. originally, our time was this bizarre thing, and our space was this very nice thing. We switched over to having sort of like a associated dynamical system whose time is easier, but whose space is complicated. Okay? There's typically a trade-off. If you have a complicated situation, complicated problem that you're trying to solve, it doesn't matter how you sort of like reformulate it. If it is complicated, there is no free lunch, is what people would say probably. There's theorems about these in computer science and everything. You can sort of like rephrase things to make it obvious. You can make it so that it's slightly more obvious though. So sometimes that works. Okay. So here's a definition. If I have a B-IFS, which is this W acting on X, and instead of writing it like this, I'm even going to drop this brackets here to make it fast. The upper similarity dimension, so this is our first notion of dimension in this class. We're going to see 5 or 6 of them and how each of them sort of like relate to each other. The upper similarity dimension of the IFS itself is the unique number, which I denoted here by d of w, that solves this equation. Okay? So I know that each of these numbers, Lipschitz constants, are each of them is less than 1 because they are contractions by definition. And I take them to, I raise them to the power t. T is my variable. Then I add them up. Okay? So the left-hand side is a function, and I'm looking at the t value such that the left-hand side becomes 1. Okay? So here's an exercise about this. If I have k numbers, real numbers, between 0 and 1, and if I were to look at this function, that's a decreasing function. So let's say a1, a2, dot, 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 ak be numbers between 0 and 1. Yeah, let's write it like this. Then let's define a function, phi of t, ai to the t, I from 1 to k, is a strictly decreasing function, is a strictly decreasing and continuous function. Okay, this is a calculus problem if you want, but I have this so that this does make sense, this word unique. Because when you think about this, this is sort of like the abstract situation over there, right? At t equals 0, so this is t. At t equals 0, well, I'm just adding k times 1, which means that I start at k. And then your job is to show that this is decreasing. Well, it's more than continuous, actually. It is differentiable and everything. So you can take the derivative, blah, 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 all that stuff, and show that this is strictly decreasing, which means that as I increase t, this function decreases. And in fact, the limit is going to be 0. In particular, if this is height 1, there's a unique time where this becomes 1. This is that unique number. Okay? So this is a nice exercise. Any questions about this? Yes?
Can I get a little bit more information on the Lipschitz distance that we're working with?
Lipschitz constant, yes.
Or the constant.
Yes. So let me just give an example. It's better. So this, these two maps we put them in sort of like an IFS, and we were talking about this, and this is, I told you that this is an example of a B-IFS. And today we're really trying to connect this to the Cantor set. Well, I'm trying to look at this when it comes to the Lipschitz constant. I look at 2 points, okay, and I look at the distance between them, something. And then I apply to both of these points the same transformation. They go to somewhere else. Then I measure the distance again, okay? Now, I want this, okay? So if you were to think about this, this is the distance between their images. And oh, I guess this should be a y. And here is the distance between the original points. Now, I want to relate the 2 expressions, and this should be 1. Sorry. I'm applying the same transformation to 2 different points. Well, this is nothing but x over 3, and this 2 is nothing but y over 3, which means that this is nothing but x minus y in absolute value divided by 3. And so I want to think of it as this. Okay, so this is a contraction is what I'm saying. Takes 2 points and contracts the distance between them by this number. Okay, so far? So this is a contraction, and this is part of what it means for a function to be a contraction. But here's a problem, though. If I were to put here 2, this statement is also true. But in a sense, this is more true. Okay, this is better. Gives you the best constant that you can put here. That best constant is the Lipschitz constant.
And that's what we're looking
Yes.
to
Yes.
narrow in on, right?
Yes.
Okay.
Yes. Okay, so let's continue with this example. Let's try to compute the upper similarity dimension. Now, at this stage, I don't even have the Cantor set. I'm still talking about the dimension of something, but it's the dimension of this dynamical system, if you want. And at the same time, I'm sort of trying to stretch the notion of dimension that you would have. Yes?
I think I'm a little confused on what you mean by this is the number that solves this specific equation right here.
Let me finish the
I'll
example.
let you-
Yes.
I'll let you do the example.
Okay, this is our example. This is my first transformation, my second transformation. They are both contractions acting on the complete metric space R. Okay, let me erase this. The Lipschitz constant of both of them is 1 over 3. Now remember, this constant has to work for any 2 pairs of points. Maybe some other points get even closer. That's not my problem. I need a constant that works for any 2 pair. So now I need to write down this equation. So this to t is 1 over 3 to the t plus, well, the second one has the same constant, equals 1. Okay, so this is nothing but twice. So 2 times 1 over 3 to the t equals 1. This is the same number. Send this 2 to the other side. Okay, take logs. So I'm trying to solve for t, this equation. If I were to take logs, well, the log takes the exponent and turns it into a multiplication. Okay, which means that solving for t tells me that t has to be log of 1 over 2 divided by log of 1 over 3. Well, I can think of 1 over 2 as 2 to the minus 1, and this 2 has a power of minus 1, which means that I can cancel them out and get that the upper similarity dimension of this particular B-IFS is log 2 over log 3. It's a number. And I'm saying this is supposed to be some sort of a dimension. Is this sort of starting to make sense?
I think that makes sense now.
Yes.
For some reason, I had some notion that the dw needed to be somehow related to that equation more than it's just
No.
the answer. But
Yeah.
not unrelated.
Now later on, so we have already seen, in fact, this number before. I told you that the dimension of the Cantor set, this middle thirds Cantor set, is this number. When I was talking about that, I was actually talking about a different notion of dimension, which is this Hausdorff dimension. We're going to discuss that later, and we're going to have this theorem by, on the syllabus I called the Hutchinson formula, but it turns out that Moran, like a long time ago, did prove it back in the 40s. So Moran, I guess Moran/Hutchinson formula says that under certain circumstances, the upper similarity dimension of a B-IFS equals the Hausdorff dimension of the attractor, which is going to be this Cantor set type of set. Okay, that's going to come later. Any questions about this so far?
Can you have like infinite operators in like your W though?
A priori, yes, but not in this context. So we're just looking at finitely many to make things easier.
Yeah.
But yes. Any other questions? Okay. Now here's an exercise. Let's try to do the same thing with the Sierpinski gasket. I think that's what one is supposed to call it. So this is not the set itself, but it's something related, right? Like I want to come up with a B-IFS that probably is related to the Sierpinski, and then of that IFS, I want to compute, or I want you to compute the upper similarity dimension. So when we were talking about this, we started with this, and we got rid of the triangles like this and so on. But to handle this formalism, we really need specific formulas for these pieces. So instead, this is slightly easier to do. Let's look at it like this. I'm going to put my Sierpinski like this, and I'm going to get rid of triangles like so. It's basically the same shape. Okay. So now my capital X is going to be R2, the plane, and I need some transformations based on the idea that really I'm starting with the triangle and I'm getting 3 smaller copies of it. I have the sense that I should have in my IFS 3 different transformations. Okay. Now the first one, let's say, is going to take things and shrink everything to here, or shrink the triangle to here, which means that this should be, or maybe we should use this notation, because my points are on the plane after all. Well, I need to scale both of the coordinates by a factor of 1/2. Okay. Any questions about this so far? So this is supposed to handle this piece. Now I need another transformation that handles this piece and another one that handles this piece. Any guesses as to what they could be? So let's say that W2 is handling this piece.
The right one?
Yeah, this triangle.
Do 1/2 plus x over 2 comma y over 2.
Yeah, right. So you start with this and then shift it this way. Shift it horizontally. So that means that you need to add what 1 over 2 to the x coordinate. And if I were to do the same thing for this guy, I would need to add 1 over 2 to the second coordinate. And here I didn't write, of course, but this point is supposed to be 1, 0, and this point is supposed to be 0, 1, and so on. And this is supposed to be 1 over 2, comma 0, and everything. Okay. Now, is this a B-IFS? I have 3 functions acting on the plane. Are they contractions? Yes.
Usually, yeah.
Right? Because they all shrink by a factor of 2. Okay. Which means that this constitutes a B-IFS. And then I can ask then the upper similarity dimension. I'm going to leave that to you. Okay, that's a nice exercise. Apply the same reasoning. You look at this function, or rather you look at this equation for this guy and solve for t. Okay.
So
Yes.
if they were different, like W1 is different from W2, you would pick the biggest one, right?
No. That's the thing.
Oh, you still have to add them all up and then solve it.
Yes. Yes. So let's say that this is the interval. Let's say that the first transformation does this, which means that it shrinks by a factor of 4 or 1 over 4. And the second transformation does this, which means that it shrinks by a factor of 1/2. Then to compute, and this is again a B-IFS. See, I have different constants, but it's okay. As long as everything is a contraction, that's fine. To solve this, let's write it like this. I would need to solve the following equation. So the contraction constant for W1 is 1 over 4 to the t, and the contraction constant for the second guy is 1 over 2. Okay. And here, there's still some, similarities here because I can expand this by a factor of 2. I can write it as 2 over 4 and possibly solve it. I'm not saying that in general you're going to get this very nice number, okay? But certainly it is a unique solution, which you can approximate as much as you want with a computer if you want it, okay? Any questions about this? So if you want, let's write it like this.
Is there some sort of like, what's the reason behind calling it an upper similarity dimension? I guess maybe I don't understand exactly what it deals with dimensions and how it helps with knowing about its dimensionality.
Okay, so what I told you is that under certain circumstances, this Hutchinson-Moran formula that we're going to discuss later does tell you that this number is the Hausdorff dimension.
Okay.
It's the same number that some other weird dimension gives. Okay, so this is like part of dimension theory. You define 75 billion different types of dimensions, and then you have all this work. Oh, is this the same as that one? Under which circumstances are these the same? Yeah. That's the whole industry. You define things and then you try to compute. And then you cannot compute, and then someone else comes up with sort of like a different thing that is more computable. We're going to see more and more. But why the upper? That's a good question. Because I can do silly things with the IFSs. Okay? So here's another example. I want to leave this here. So in this example, I can just add yet another function to this business. That is like kind of bizarre. Let's say that yeah, so for instance, I can do 3, which let's say is x over 6. And I have this third guy. So now you see the problem, I hope. This is a perfectly valid B-IFS. I can look at the Hutchinson operator. I can do everything. But you see, this is slightly pathological because even if you were to consider the interval, this guy and this guy, they're sort of overlapping. Okay? So ultimately, you would probably expect that, or maybe let's do x over 9. That's easier. So this squared. Ultimately, you would want to get the same Cantor set, and we're going to see that it does generate the same thing. But if you were to compute the upper dimension, upper similarity dimension, now you need to solve this equation. Well, the solution to this is not the number that we came up with. It's not log 2 or log 3. It's some other number, but it's a different number. But somehow, this is sort of like a redundant transformation. Okay? So I sort of like, on a whim, I just increased the dimension here. Because now this function starts at 3. The previous one started at 2. Okay, that's the issue. And the problem, indeed, is this, that these two have what we're going to call overlaps. And that Hutchinson-Moran formula says that if your B-IFS has no overlaps, essentially, then this dimension is the same thing as some other dimension, which is this Hausdorff dimension that we're going to define later. Okay? Is this sort of making sense a little bit? Okay. Any other questions? Okay. I want to introduce one more thing, which is the Hutchinson operator with condensation. This is, from an abstract point of view, not that sophisticated of an idea, but when it comes to applications and graphics and image processing and stuff, it becomes very useful. So I wanted to mention it, and Barnsley sort of like goes into this as well. But the math doesn't really change that much when you switch over from the standard Hutchinson to Hutchinson with condensation. Okay. Let's say, so I have a B-IFS, and then I take some other set that is compact and non-empty. So this K is what I'm going to call the condensation set. Then B-IFS with condensation, or Hutchinson with condensation. Is by definition this operator. So as inputs, it takes the IFS and the set that you fixed. And it's acting on the hyperspace. And all it does is that instead of just taking the unions of the images of your set that you feed to it, instead of only this, it also takes the union with this and K. Maybe I should use a different letter here, L. So this is my operator To it, I feed a point in the hyperspace, which is yet another set, but never mind. And then you take the union of everything. So L union that's what you do. Okay. It's just another function. Later today, I want to sort of give an example as to how you might use this idea. And here, L is said to be the condensation set, but let me not write it down. Any questions about this so far?
Can you remind me, you discussed condensation a little bit last week.
Yes.
What was it again?
What I said last time was that if you were to fix this, so, okay, let's write it here. I said that this transformation is continuous. So you take an A and take the union of A with 0, 1. So this is sort of like a related idea, if you want. Yeah. And just whatever set you have, it's a shape, you put the interval in it. You adjoin the interval. Any other questions? Okay. So, okay, now I can state again the Banach contraction principle. It is our main theorem for this part. It's not as complicated as the completeness theorem that we were discussing before, but it's still very useful. Maybe I should ask, how many of you have seen this contraction principle? Maybe you've heard of it. Okay, good. So I'm going to write this contraction principle. I'm not going to prove it. I'm going to switch over to Hutchinson's theorem, which uses the contraction principle to get an idea as to how one might use this theorem. And then we're going to go back and prove the contraction principle. Oh, even before that, maybe I should define certain things. Yeah. Let X be a set and F be a transformation, a function from X to itself. So it's a dynamical system. I keep iterating F. Well, I'm going to call a point in X to be a fixed point of F if f of X equals X. Fixed point of F if this is sort of like the notion of equilibrium solution, equilibrium state, and all that stuff in differential equations, for instance. And I'm going to call it a periodic point of F if, well, the same equation holds, but for some power of F. So maybe not after applying it once, but maybe you applied 3 times and then you get back. Of F if there is some integer p such that F to the p of X equals X. Okay. Now the sets of fixed points and periodic points I'm going to denote by fix of F and per of F. Which is the union, if you want, of all fixed points of all iterates of F. So these are, you see, 2 sets that you associate to a dynamical system that are important. So maybe we should do an example. Let's look at the doubling map. Recall that this was defined like so, 2x mod 1, and its graph looked like this. I don't like these things. It's just that there's these like stubs that I end up having so many of, and then there's no way of writing with them. So, and then anyway. So this guy looks like so. What are the fixed points of this transformation?
0, 0, 1, 1.
Right, you can solve the equation. You can say, I need 2x equals x mod 1. That is to say, x has to be 0 mod 1. Well, there are only 2 points like this. And on the graph too, you can see these points as the intersection points of the graph of f and the main diagonal. That's the geometric way of interpreting this. So this is f, and this is the main diagonal. And this gives you these 2 points. Okay. So you don't want to say 0, 0 because I'm sort of like drawing the space 2 times. It's 0 or 1. Does this make sense? Okay. Are there any other periodic points? Of course, fixed points are periodic, right? Because if f of 0 is 0, then f squared of 0 is also 0. But maybe there's a period 2 point. Okay, so I'm asking for points. Let's keep writing it over here. This is a very basic example, but it's already very deep, this thing. So what do I need? I need this now. Well, last time we discussed that applying f twice, which is the time 2 map of the dynamical system, is just 4x mod 1. Which means that I need to look at 3x equals 0 mod 1. Okay. And so what could this be? Certainly 0. Okay. So when I'm looking at the fixed points of the time 2 map, I need to count the fixed points coming from the time 1 map also, because if these 2 points are fixed in one time, they're fixed for any time. So I start with 0. What other solutions are there? Well, if I were to plug in 1 over 3, I get that, and 2 over 3, and then 1. Okay. Let's check that this matches with the geometry, because we can also draw this function for x mod 1. Okay, this is my time 2 map. Well, how many times does the graph of f squared intersect with the main diagonal? 1, 2, 3, 4. It doesn't quite say what the numbers are, but at the very least, it says something about the numbers, the number of things that are in this set. Cool. So, as an exercise, what are the fixed points of the nth time n map? Find the numbers. Any guesses as to how many elements, how many points should there be in this set? Yeah, that's sort of the guess, but
I had 2 data points. That's all I need.
yeah, exactly. It's like 2 steps is fine. Very small sample size. N equals 2. This is like a law of nature. Okay. So we're going to sort of like study this even further, this idea of a fixed point and the periodic point and everything. Let me just add one more thing. Here's the bizarre definition. So for each time n, you can look at this set. And further, you can sort of reduce the set to the number of things in it. Okay? So you have, in a sense, a sequence of integers associated to a dynamical system. Dynamical system in this sense, iterates of a function. You can do this more generally, but even this is too complicated, as you're going to see in a second. One of the things you can do to understand a sequence of numbers is to put them in a power series. And so this leads to this idea of a zeta function. Now I'm going to put these numbers in a power series, but I'm not saying anything about convergence and stuff. I'm just formally writing something. Let x be a set, x be an arbitrary function. Let's say, we need to assume something. Let's say that for each time n, or time p, the number of fixed points at time n is a finite number. Say, for each n, the number of fixed points at time n is a finite number. Then the zeta function of f is the following. It's a formal function. I'm not really thinking of it at this stage as a function, but still, that's what people call it. I'm going to do this. At first glance, it looks kind of bizarre, but bear with me. So maybe I should write it like this. N from 1 to infinity. So I started with this expression. T is my variable. I'm going to multiply the nth term here with this number. Then I'm going to take this whole thing and take its exponential. Okay, now, this is a bizarre thing. I'm not claiming that it's easy to understand. I'm not expecting you to be familiar with this. Let me just say that this is somewhat related to this Riemann zeta function and stuff like that. It's a generalization in a sense. It apparently started with Andre Weil, and then Artin and Maser adapted it to dynamics. And I wrote some more names. And then Ruel and other people took this even further. Ruel, Perry, Polycott. And goes on and on, okay? So these are what are called dynamical zeta functions. This gets even more complicated than this, but there's papers under the resources written by these people. If you're interested, you may want to have a look at. I also put a set of lecture notes by Milner You may also have a look at that. He explains this, I think, very well. So at this stage, let me just say this. Okay, why someone would do something like this. So first of all, this is something like a Laplace transform. Okay, so if you took differential equations, you know that you can start with a function and you can take the Laplace transform of the equation and things sort of like change and like it becomes easier to solve somehow. This is sort of like a discrete version of it. Perhaps it's better to call it the Z transform. That's the first thing. Second, this is a formal expression at this point. You're not saying anything about convergence because whenever you have a series, you want to say, oh, what is the radius of convergence? What is its zeros as a function? What is its poles? When does it blow up and everything? And somehow, it turns out, those numbers, radius of convergence, number of zeros or the positions of zeros, or the poles, number of poles or the positions of poles, say non-trivial things about the dynamical system that you started with. Okay, so this is like a very fruitful endeavor. It's also very deep. I know some of you are taking complex analysis, it's related to that, and some of you are interested in number theory, that's also related to that, of course. Okay, any questions about this? I just wanted to introduce this idea, but maybe we'll discuss more, but I doubt it. I hope that some of you are going to take this and discuss it in reports or perhaps in the final report. Yes?
Do you have enough knowledge about the Riemann hypothesis
No.
to tie it?
No.
Okay.
No. No.
I appreciate the honesty.
Yeah, no. I know very little number theory. Any other questions? Let me just say that there is this other person, and I put some papers by him there as well under the resources. Goes by the name of Lapidus, that's his last name, I guess. This is the nickname. He also sort of has these, has these zeta functions, but they're different, okay? So he has what is called fractal zeta functions. And somehow, using those, he can come up with notions of dimensions that are actually complex numbers. Okay, that's sort of like a even more sort of abstract, perhaps, at least to me. These works I am more familiar with. Okay, so this really becomes sort of one of the starting points of what is called thermodynamic formalism. So Ruel and other people like Sinai back in the, I guess, 60s, they were interested in statistical mechanics and thermodynamics, and they were able to sort of import some of those ideas into abstract math. And this is sort of like how we do dynamics nowadays, because we have all these like physical tools that are applicable in the abstract setting. You can take a problem from number theory, think of it from a dynamical point of view, do thermodynamics with it, and then say something about the number theory itself. So it's like it's a very interesting sort of endeavor, as far as I'm concerned. Any questions about any of this so far?
Who is the person with the whole thermodynamical?
I would say Ruel, and the other name would be Sinai probably. Yeah. Yeah, I mean, it's fair to say that Pessin, for instance, one of whose books is in the syllabus, it's fair to say that he's somewhat of a student. Even if he's not an official student, he certainly learned a lot from Sinai. So it's like a whole like ancestry thing going on. And when I was in grad school, I took thermodynamic formalism from Pessin. So I didn't understand it then, but now I think I'm starting to understand a little bit. But okay. So, okay, I didn't write the theorem. Let me write the theorem and then we can take a break. What is all this business about? The Banach contraction theorem says something about the fixed points. contraction principle. Let X be a complete metric space. And F be a function from X to itself, just a dynamical system. If F is a contraction, so if its Lipschitz constant is less than 1, then F has a unique fixed point. And now that we discussed periodic points, let me also say that that unique fixed point is also the unique periodic point. Okay. When we come back, we're going to apply this to the context of B-IFSs through the Hutchinson operator. And then we're going to prove this and other things. Okay, let's take a break. We'll meet in 5 minutes. Okay, welcome back. Let's continue. Okay, Banach contraction principle. Any contraction on a complete metric space has a unique fixed point, which is also the unique periodic point. We're just going to take this as a black box for now. The proof is not that complicated. I want to sort of highlight how it is used in this context, because I think we've been spending too much time on formalisms and abstractions and blah, blah, blah. But this is sort of like what we were building up to. Here's an exercise though. If I have a transformation f on x, as in the Banach contraction principle, find a closed formula for the zeta function of it. Okay. Well, this is saying that you have a unique fixed point and unique periodic point, which means that you see this term here vanishes because the number of fixed points of f to the n is always going to be 1. Okay, you're not going to have this, and your zeta function is going to be e to this sum. Okay. Now it turns out that there's a closed formula for that. I think you're going to end up with something like 1 over 1 minus t. Because this is basically the power series for log of 1 minus t or something like that. You need to sort of look into this. But it's a very nice exercise. Okay, so now we have the Hutchinson theorem. It says that if I have a B-IFS, and let me just remind this, what I call a B-IFS is what is called in the book a hyperbolic IFS. It's the same thing. It's just that an iterated function system could be more general, like your colleague suggested. It could have infinitely many transformations or whatever. But for us, we're just looking at this type of iterated function systems. I'm not saying there isn't theory for more general things, but we're not looking at those for now. If you're interested, I put a lot of papers under the resources, which sort of like look at more complicated results and all that. Hutchinson theorem says that if you have a B-IFS, then there's a unique set that is compact and non-empty. It's a unique subset of X that solves this equation. So you're thinking of it as an equation whose unknown is a set. Okay, the conclusion is that this is a unique set solution. Okay, and indeed, here's an exercise. Once we go through this proof, after we go through this proof, you might try doing the same thing for Hutchinson operators with condensation, verbatim, the same proof is going to work for those. It's just that it takes some time to write it again. I'm not going to write it for Hutchinson operators with condensation, but I'm leaving that to you as an exercise. Okay. Any guesses as to how I could prove this?
Can you say that there's this fixed point that's shared amongst them, and then somehow construct something along? Actually, that doesn't make sense.
You're almost there.
Did you say that like they're all points in the hyperspace, so like the union of them is also in there?
Well, that is true. But
Is the union the problem?
so how do I use this? I need a transformation. What is a transformation on the hyperspace? What is the transformation on the hyperspace? There's a reason why I call this the Hutchinson theorem.
That's just an operator?
Yeah, Hutchinson operator. Okay, so this right-hand side is the Hutchinson operator applied to a transformation. I'm really asking for a fixed point for the Hutchinson operator. Okay, so fixed point in the hyperspace for the Hutchinson operator. Right, because this equation literally says that A star equals H of W of A star. This is what we need. Okay. By definition, because I started with a B-IFS, I know that X is complete. Now, from last week, we know that if X is complete, then so is H of X. Okay? So let's look at the ingredients. So the X here is going to be H of X for us. So this is okay. I have a transformation from this space to itself. It's this Hutchinson operator. We have that. Okay? What we need is this. This is what I need. So the only thing that I need here is that the Lipschitz constant of the Hutchinson operator is less than 1. That is to say that it's a contraction. Relative to what? Well, relative to the metric with respect to which this guy is complete, which is the Pompeo-Hausdorff distance. Okay, so that's what we need to prove. So it suffices by this, the Banach contraction principle, that the Lipschitz constant of the Hutchinson operator is less than 1. Okay? Now that's what I'm trying to do. The moment I can show this, this machinery is going to tell me that this has a unique fixed point. That unique fixed point is in the hyperspace, which means that you have a unique set that solves the equation. Okay. And this isn't really that deep. So let me remind you an exercise that I had given you. It said something about the Pompeo-Hausdorff distance between unions of sets. This is bounded by the max over I of the Pompeo-Hausdorff distances between AI and BI. Okay. Now, Here's another exercise now. If I were to take two functions, compose them, and if I were to look at the Lipschitz constant of their composition, that Lipschitz constant is bounded by the products of the Lipschitz constants of the individual functions. In other words, the Lipschitz function or Lipschitz constant is submultiplicative. Okay. Now let's look at this then. I have here k many contractions. So what I can look at is the following. I'm going to factorize the Hutchinson operator. So here is the Hutchinson operator. And here I'm going to have this guy. Hyperspace multiplied with itself k times. It's the set of all k tuples of compact subsets. Let's call this phi. And let's, so okay, let me just leave that as is. Or let's call this psi. Okay. So how does this guy work? Take a set A. From this, I need k different subsets. Well, those k different subsets are going to be each and every single one of these. Okay, and then what is this function? This function goes from here to there. What does it do? It takes a tuple of sets, takes their union. Okay. Is this clear that indeed this Hutchinson operator is first taking a set, then taking these images, which gives me a tuple of sets, and then taking their union, so that this composition does indeed hold. So psi composed with phi. Now in the book, there's a slightly different proof, but it's basically the same idea. I'm sort of like doing a more slick proof without, trying to do any calculations, but it's basically the same idea. Okay. Now I want to apply this exercise to this. So now my Hutchinson operator is its composition, and I'm bounding it by these two things. Well, this exercise says, really, that the Lipschitz constant of this map, which is the union, is bounded by 1. Okay, let's write it over here. I am doing my best to confuse you in this proof, but we should go and read this in the book as well. So by the exercise, this is bounded by this. So that's the first guy times the second guy. Now this is bounded by 1. What is this Lipschitz constant? Well, now I can apply this theorem, or this exercise to it. Okay, now I'm looking at the distance in this space of tuples, and let's use the max distance there. So this is, by definition, the max of the Pompeo-Hausdorff distances when these terms are compared entry-wise. Okay, then you open up the definition of this Pompeo-Hausdorff distance, and then you realize that because this guy, the WI map, is a contraction, this Pompeo-Hausdorff distance, you can use this min-max definition for this, for instance, is bounded by Lipschitz constant of this WI map times the Pompeo-Hausdorff distance between the two. In case this is confusing, that's an exercise. But then in this expression, this doesn't depend on the index, which means that I can sort of take this out. And indeed, each one of these is bounded by 1. Or let's not write it like that. Let's write it like this. Okay. Now this really says that this first part of the Hutchinson operator is a contraction, because this number is a number that is strictly less than 1. And here I hope you can see why using finitely many maps is useful, because if I had infinitely many, even though each one of them is a contraction, I could have approached 1, and I didn't want that. I'm not saying that it doesn't work there. I'm also not saying that it does work there. I'm being a politician here, okay? So that means that E is a contraction. Okay. In any event, this is a number that is less than 1. Okay, that means that the Lipschitz constant of the Hutchinson operator associated to the B-IFS is less than 1. In other words, it's the contraction, which means that by the Banach contraction principle, it is a unique fixed point. And that's the end of the proof. Let me not write it. Questions about this? I still haven't proved this Banach contraction principle, but let's look at an example, okay? This Cantor set. Ultimately, finally, we should be able to sort of like relate this to Cantor. X is R. My first transformation is x over 3. My second transformation is x plus 2 over 3. My B-IFS is these two guys. Lipschitz constants is 1 over 3. That means that they're a contraction by this theorem. That means that there is a unique set which I'm going to denote by C evocatively. C such that this happens. is this believable? Well, I mean, I'm saying the only set, I'm not saying that this C is the Cantor set, by the way. Okay, the Hutchinson theorem just gives you existence. It's like the existence and uniqueness in the context of differential equations. Just because you have the unique solution doesn't mean that you know what that is. You know that it exists. Existing is not the same thing as being known. It's a different thing. But let's try to identify that this unique fixed point, this unique set, is indeed this Cantor set. Now, first of all, obviously this equation is solved by C equals empty set. Empty set equals, well, empty set union empty set. Is it a problem? Well, it's not a problem, except that the empty set is not here. Okay, so is the reals. The reals also solve this, but it's not in the space of solutions that I'm trying to look at. Okay, so now I'm trying to understand that this middle thirds Cantor set that we've been looking at for so long now is indeed this unique fixed point that the Hutchinson theorem gives. Well, how to justify this? Well, first of all, what does this say? It says that if I take a point in C, because W1 of C is part of C, well, this should be inside my set as well. So no matter which number you start with, 1/3 times that number should be inside. Okay, that's fine. But the problem when you're trying to identify that this fixed point is indeed the Cantor set is that it goes backwards as well. Okay? Because C is this union this, any point you choose here must come from C itself under W1 or W2. Also, there is Y in C such that either this happens or this happens. In any event, if X is in C, then there is some other point Y, which basically is 3 times X. Because if from Y to X, I need to shrink by a factor of 3. To go backward, I need to expand by a factor of 3. But I can keep iterating this idea and see that if I have a point that is not between these two numbers, so if the C is not included here, let's say that you have a point here, then you have a point here, and you have a point there, which means that the set is not going to be compact. Okay? That's why, based on this, you can indeed see that for this particular B-IFS, the unique fixed point generated or given or guaranteed, let's say, by the Hutchinson theorem is the middle thirds Cantor set. This is like a very nice thing to think about, but this is sort of like the idea. Okay. Any questions about this? You can do this for the Sierpinski and everything.
Something that I'm confused about is originally seeing like the Hutchinson operator applied on the 0 to 1 interval. That seemed very.
I didn't apply it there. I applied it on the reals.
Okay. Well, I think
That's the thing. You can start with any Banach contraction. Part of Banach contraction principle is going to actually give you a way to approximate it.
Okay. Oh, so I think I was
Yeah.
saying that like.
Yeah. I black boxed that Banach contraction principle, which I guess we're going to do next week. But this Banach contraction principle, I'm going to write it again, and like it's going to be more quantitative in a sense. Okay.
I didn't think I was going to ask this question better than.
Yeah.
One.
Okay. Now things are sort of starting to get interesting. If things are like more abstract, I would just highly recommend that you go to the book and like start working on specific examples to understand. Okay. Thank you. Have a nice weekend. I'll see you next week.